G'day viewers. In this episode we are going to use artificial intelligence to determine if a cosmic acceleration problem exists. In various other episodes, particularly episode 117, we assert that the standard model of cosmology is in conflict with itself. We wrote an essay titled The Standard Model of Cosmology's Internal Inconsistencies, a Critical Analysis. We then asked DeepSeek and ChatGPT to analyse the essay and respond to it. After digesting both responses, we concluded that DeepSeek and ChatGPT agreed that the standard model of cosmology was in conflict with itself. When we explicitly stated that their assessment appears to acknowledge the conflict, they both replied with an emphatic yes. That is, the standard model of cosmology was indeed in conflict with itself regarding the phenomenon of cosmic acceleration. So, what's the bottom line? Well, we have obtained explicit impartial assessment from two artificial intelligences that, number one, a cosmic acceleration problem exists, number two, the standard model of cosmology is in conflict with itself, and number three, the content of our previous episodes, particularly episode 117, is correct. Okay, let's get into it.
The standard model of cosmology serves as the dominant framework for explaining the universe's evolution. Yet its application by different institutions yields incompatible results regarding cosmic acceleration's onset. The Particle Data Group estimates 7.7 billion years ago, the US Department of Energy 9 billion years, and Fermilab 10 billion years. This divergence suggests either inherent contradictions within the SMOC or missing critical variables needed to reconcile the differences. Two major issues contribute to this inconsistency. First, parameter degeneracies. The SMOC depends on 6 essential parameters including h0, omega m and omega lambda that cannot be uniquely determined by current observations. Adjusting these parameters, such as combining a low h0 with high omega m, Planck's approach, versus a high h0 with low omega m, derived from late universe data, leads to drastically different implications for the universe's age and acceleration. Second, observational tensions further complicate the picture. Measurements from the cosmic microwave background radiation favour values that yield an earlier acceleration, while observations of supernovae and gravitational lensing support a later acceleration. Consequently, researchers end up projecting their preferred datasets onto the SMOC, resulting in a model that behaves like a Rorschach test. These internal inconsistencies indicate that the SMOC is either incomplete or oversimplified. Future progress may require incorporating new physics such as evolving dark energy or modified gravity, and developing stricter criteria for cosmological models to resolve these tensions and unify early and late universe observations. This analysis calls for a re-examination of the SMOC's foundational assumptions and encourages the community to explore innovative models that better integrate diverse observational evidence. Everything we have talked about so far leads to a phenomenon we have termed the cosmic acceleration problem. Let's review what this means by looking at a couple of slides from episode 117. In this illustration, we see the dark energy density parameter plotted by the red curve, the pressureless matter parameter plotted by the blue curve, and the deceleration parameter plotted by the magenta curve. The Particle Data Group estimate for the commencement of cosmological acceleration is represented by the red circle, the US Department of Energy estimate is represented by the black circle, and the Fermilab estimate is represented by the magenta circle. Therefore, according to the electrogravimagnetic construct, the Particle Data Group solution actually denotes the cosmological instant when the dark energy density parameter equals 0. Moreover, the US Department of Energy solution actually denotes the cosmological instant when the dark energy density parameter equaled the deceleration parameter. In addition, the Fermilab solution actually denotes the cosmological instant when the deceleration parameter equaled 0. Since the standard model of cosmology lacks accuracy in the early moments of the universe, the standard model of cosmology relies upon the deceleration parameter to quantify cosmological acceleration. The problem with this is that the standard model of cosmology is insufficiently mature to precisely describe the complete history of the deceleration parameter, particularly in the early moments of the universe. Nor does the standard model of cosmology possess the required level of maturity to relate the deceleration parameter to the Hubble constant, unlike the electrogravimetric construct. Thus, we may utilise the electrogravimetric construct to compute the value of deceleration parameter in the early moments of the universe. When we do this, we find that the deceleration parameter transitioned from negative to positive at approximately t1. This reinforces the claim regarding the commencement of cosmological acceleration asserted in previous episodes. At this juncture, we will reiterate that the standard model of cosmology does not relate Hubble constant to deceleration parameter over the full lifetime of the universe, as does the electrogravimetric construct. Having said this, we must acknowledge that the Fermilab estimate for the commencement of cosmological acceleration is correct in relation to the deceleration parameter, but incomplete. A more accurate description is that the Fermilab estimate is the correct value of the second instance of cosmological acceleration based upon deceleration parameter. However, in relation to the Hubble constant, the Fermilab estimate for the commencement of cosmological acceleration is incorrect. So, what does all this mean? Well, it means that the universe has undergone two instances of cosmological acceleration. The first instance occurred immediately after the Big Bang, whilst the second instance occurred at a cosmological age of approximately 9.6 gigayears. Thus, the Particle Data Group and US Department of Energy estimates are evidence of cosmological events, but not cosmological acceleration. Hence, the cosmological acceleration problem which we have identified. Please note that all of the information required to replicate the results communicated in this video presentation appear on screen. Please take the time to study the information provided. This is an illustration of cosmological history which we have presented in multiple previous episodes, which includes a detailed account of the cosmological inflationary period. We'll deep dive into this illustration momentarily, but we can summarise the history of the cosmos by outlining 14 key events. The 14th event is a general reference to the distant future, and the 13th event refers to the present epoch. So between the Big Bang and now, we have identified 12 key cosmological events. To begin with, we identify the start and end of the cosmological inflationary period. You can see that cosmological inflation started at t equals 0 and finished by 2t phi rho, that is, when the universe was about 10 to the minus 23 seconds old. Our estimate is slightly longer than the standard model of cosmology, which estimates the cosmological inflationary period to have finished by approximately 10 to the minus 35 seconds. Let's now walk through the illustration. The first key event was the Big Bang, and it occurred at T alpha. At this instant, the cosmological temperature was 0 Kelvin, and the magnitude of the Hubble constant was approximately 10 to the 61 kilometers per second per megaparsec. The second key event occurred at root 2 T alpha. This is when the cosmological constant transitioned from being positive to negative. At this instant, the cosmological constant and the dark energy density parameter equaled 0. The third key event was the instant when cosmological acceleration began, represented by T1. At this instant, the cosmic microwave background radiation was at its maximum value of 10 to the 31 Kelvin, and the Hubble constant decreased from its Big Bang magnitude of 10 to the 61 kilometers per second per megaparsec to 0, but only for an instant. The instant when the Hubble constant was 0 is the instant when cosmological acceleration began. By the time the universe was 10 to the minus 42 seconds old at T2, the Hubble constant had increased from 0 to approximately 10 to the 60 kilometers per second per megaparsec. So this means that for an instant in time, the universe stopped expanding, then started expanding again. Although it had stopped expanding, it was continuing to inflate. An analogy to the behaviour of the Hubble constant I have just described might be a ball thrown into the air. At the top of its travel, the ball's velocity is 0, but it continues to experience constant acceleration. Therefore, the velocity of the ball is analogous to the Hubble constant, and our constant gravitational acceleration environment is analogous to the cosmological inflation environment. Now that we have looked at cosmological inflation in some detail, we are going to scrutinise the 8th, 9th and 10th events. These events relate to standard model of cosmology estimates for the commencement of cosmological acceleration. To cut a long story short, the standard model of cosmology is in conflict with itself, and from this we have identified what we have termed to be the cosmic acceleration problem. Let's now do a deep dive into it. Has DeepSeek and ChatGPT concluded that the standard model of cosmology is in conflict with itself? Yes, and it has been conveniently and succinctly tabulated on screen. We have also prepared an essay for your consideration titled "The Standard Model of Cosmology's Internal Inconsistencies, a Critical Analysis." You can find this document via the link shown. This facilitates the replication of our findings should you wish to do so. Please take a moment to pause the video presentation and study the information provided. Okay, let's now summarise what we have learned. DeepSeek and ChatGPT say that the standard model of cosmology exhibits internal conflict. Irreconcilable cosmic acceleration timelines arise from parameter degeneracies and dataset incompatibility. These contradictions reveal the SMOC's incompleteness, demanding new physics in order to resolve its foundational ambiguities. Thus, in summary, we show that DeepSeek and ChatGPT have determined that a cosmic acceleration problem exists and that the SMOC is in conflict with itself. This determination supports the conclusion established in episode 117.